No, no, you're not wasting your time. No, you're not. All right. I understand a few of you have a chemistry celebration in the business building, and so given the walk, let's go ahead and get right to it. All right, lecture 10. Just so everybody is aware, this is the last concept lecture on exam 1, okay? This is the last thing that we're going to cover is static equilibrium in 3D, okay? So really up until now, we've been like doing everything in 2D, and this week is just applying what we've done in 2D and 3D in the third dimension. So Monday we did, here's how to add vectors in 3D. And today what we're going to do is, here's how to figure out unknown vectors to meet static equilibrium. Okay? So I don't think that today is really going to be all that mysterious. I think like it's an exercise that we need to do, but like I'm a fan of completing topics, but if we wanted to say you can figure this out on your own, you probably could. But I don't want to do that with this. I want to go through it. Okay. But yeah, this is the last topic on the exam. Now I have here being graded. I think a few of these assignments are graded. I didn't get a chance to check right before, but I know my TA was grading a lot of stuff this past evening. For the assignment that's assigned today, it is due Friday. I'm going to turn the solution on Saturday. Okay, usually I wait till Monday, but I'm going to turn it on Saturday so that you all have it to look at for the exam. Okay, does that sound good? All right, any questions? Let's jump in. Did everybody get the code? Okay, so just so everybody is aware, I put this slide here. This is the slide from the last lecture. The one thing that was missing on that slide was this, but we covered that on Monday. So the idea is that if you want to determine orientations in 3 dimensions, that the unit vector, the terms of the unit vector are just the cosines of the angles of that vector from the x, y, and z axes respectively. But the point of this slide is really to illustrate the similarities between 2D and 3D. That really it's just the same stuff, just a little bit more. You know, instead of 2 equations of equilibrium, you have 3. Instead of I and J, you have I, J, and K. You know, but it's the same idea across the board. Granted, I think we all know it takes a little bit more work to get to the force vectors, but once you get there, it's pretty straightforward. We're going to do a 3D equilibrium problem today. Okay, and it is really going to be pretty straightforward. It's going to be pretty methodical, pretty rote. We are going to have a 3x3 system of equations to solve. I'm not sure if everybody brought their calculator with them today, but I'm going to do a lot of that part with everybody today. But just know that if you have your Casio, mode 5.1 is the 2x2 system, mode 5.3 is the 3x3 system. So it's the same process, it's the same idea. And like I said, I want to get into it, especially because I know a lot of you have a chemistry exam. So let me go to the notebook here. And what we're going to do is we're going to investigate the equilibrium of this hot air balloon. So we have a hot air balloon that is being held in place by 3 cables. Okay. Now what we know is that the balloon exerts an upward force of 800 newtons. So by the way, looking at our coordinate system, if I were to describe the vector for the balloon, right? The balloon vector, it would be 800 times what? Here's our axes. So if the balloon is exerting an upward force, it's 800 J, right? It's a J vector, right? Because it's going up, it's going in the direction of the y-axis. What we are going to have are 3 vectors pointing down, okay, or down-ish, I guess I should say. We're going to have an AB vector, an AC vector, and an AD vector, a tensile force, a TAB, TAC, TAD. And what we're going to need to do is figure out what are those forces in these 3 cables in order to achieve static equilibrium. So 3 equations, 3 unknowns, okay? So let's get to it. So just to make sure we're all on the same page, we know that the magnitude is 800 newtons, and our free body diagram is really straightforward. We just have, point A. We have an upward force, which I'll call this upward force FB for the balloon. And then we're going to have 3 unknowns. Bless you. And by the way, I am getting over a sinus infection myself, so if I'm a little slower today, my apologies. Okay. All right. Is everybody okay with this? Okay. All right, am I good to scroll away from my free body diagram? I don't think there's like a lot there that's hard to interpret. Okay. Okay. All right, if you recall, distance vectors are needed because if you want to describe a vector in 3D, the easiest way of doing it is first get a distance vector, then divide by the length to get a unit vector, then multiply by the magnitude to get a force vector, right? So what we need are distance vectors for AB, AC, and AD. Okay, so I'm sort of drawing it like this because, again, I think we all agree that the most difficult part is this part. That if you can identify the distance vectors, that the rest of this should be pretty mechanical, okay? So let's see what we can see. Here's the balloon. I'm curious, is there one term on these vectors that we think is going to be the same for all of them? The y vector, the y component. What is it going to be for each of these?
Is it 5? Negative 5.6.
Now 5.6, but is it positive or negative? Negative, because we're going from A to B, A to C, A to D, and we're going to go down. So this is going to be negative 5.6. So does everybody see that we're going down? Okay. Any questions on that? All right. Let's take each axis one at a time, because maybe we'll be in the same headspace if we do that. Okay. Let's start off with the x-axis. So if I go from A to B, okay, now keep in mind the x-axis is this axis right here. This is the axis I want you paying attention to, this one. Okay. And positive direction is this way. So that's positive, okay? So if I go in the positive direction that way, let's start off with AB. What's this value going to be? Negative 4.2, exactly right. What about AC? What is AC going to be? Positive 2.4, exactly right. And what is AD going to be? 0, exactly right. See, this isn't so bad, right? It's pretty straightforward. Okay. Let's do Z. Now keep in mind, now I want you to pay attention to this one. And whenever you see the letter, like the X, the Z, or the Y, whenever you see the Z, that means that this way is positive. Okay? So let's start off with AB. What goes right here? 0. What about right here? Positive 4.2, exactly right. What about this one? negative 3.3. Does everybody see that? So this is 0. This is positive. This is negative. Again, I do believe, I think that this is the hardest part of this entire problem. Okay? The hardest part. Okay? If you understand this, the rest of this should be pretty plug and chug. So I want to take a second, and before I move on, I want to make sure we are all comfortable with this. Everybody good?
I have a question.
Yes.
So the AB for the I, why is it 0?
Okay. All right. Because, all right. So here's the origin. Okay? Look at it this way. Okay, let's look at it this way. All right? Let's look at it like this. Let's say this is the x-axis and this is the z-axis. So this would be like we're in the balloon looking down, right? Okay? So if we're in the balloon looking down, the origin's point A, right? Because like point A and point O are going to be like on top of one another, right? Does that part make sense? Like if you're in the balloon looking like that. And so if you're looking at it like that, I'm going to say that point B is about right there. I'm going to say point C is about right there, but I'm going to say point D is right there. So along the x-axis, how far do you go along the x-axis to go from A to B? It's 0, right? Like the coordinates of point D would be 0 comma something. Does that make sense? That's a good question. Don't hesitate with stuff like that. Everybody good with that? Does that make it easier to see? Anybody else? Don't hesitate if you got a question. It's good stuff. Is that good? All right. So if you're good, then if you're good, here, I'll leave that there. All right. So now what we're going to do is turn these into force vectors. The first step into turning them into force vectors is to take these distance vectors and turn them into unit vectors, right? So how do we turn a distance vector into a unit vector? How do we do that? What's that? Well, I think you're both saying the same thing. You got to get the magnitude. There you go. Yeah. So unit vectors. Okay. So the way that we're going to do that is we're going to say that the unit vector is the distance vector divided by its own magnitude, and the magnitude is going to be vx squared plus vy squared plus z squared, and then the root of all of that. Okay? Is everybody okay with that? So let me ask you a question. Maybe we could do this part a little fast. Could somebody tell me what's the magnitude of AB? What's that? 7. Do I have a second on that? Okay, so this is 7 meters. Okay? So if I wanted to determine lambda AB, lambda AB would be something times I plus something times J plus something times K. So how would I do that? I would take this divided by 7, this divided by 7, and that divided by 7. What is this and this going to be? This one's going to be 3/5. And if I was a betting man, this is going to be 4/5, and that's 0. Honestly, AB is a 3, 4, 5 triangle. It's just sort of scaled differently. That's basically what this is. That's why it's coming out so neat. Okay? Now, AC AC is not going to come out that pretty, by the way. I'm just going to tell you. All right. What is the magnitude of AC? 7.4. Do I have a second? Okay. All right. So So what's going to happen with AC is the numbers are going to, I'm just going to level with you, they're going to be messy, okay? So I'm going to do 4 decimal places just so that we all kind of, it's probably a little overboard, but just so that we all recognize the numbers when we see them later in calculations. This one's going to be 0.3243. This is going to be negative 0.7568. And this is going to be 0.5676. And I'm maintaining the positive or negative inside the parentheses because when I add everything up in a column vector, I don't know, just maybe it's just, I don't know, something with me, but I think it's just a little easier to see if all the signs are all in the parentheses. That's just me. So if you don't want to do that, that's fine. Is everybody okay if I just did that, by the way? Okay. You're going to get something similar with AD. Okay. AD, you're going to get the magnitude of 6.5, so the numbers are also a little messy here. That's 8615. And that's 5077. Now, I don't want to what I don't want to do is be that professor who just blows through things like, oh, you know this, if you actually have a question. So I don't want to be that guy. So if you have a question, don't hesitate, don't, just tell me to stop. So let me move this down a little bit so it's kind of out of the way.
So just to clarify, we're just, to get the negative 0.6, we're just taking negative 4.2 divided by 7.
Yes,
Okay.
yes. So, for example, for AD, the way I'm getting these decimals is I'm taking this divided by that.
Okay.
This divided by that. So that's, it just happened to be kind of a nice, quote unquote, pretty number with this because it's 3/5 and 4/5, but it's kind of messy with these. You could leave them in fractions if you want. I'm not. Whatever you want to do. I don't care. So, is everybody okay with that? I'm guessing most students are probably end up good at just reverting to decimals and stuff like that during exams anyway, so we're engineers. So. But is everybody comfortable with that stuff? Okay. So the next thing to do is this. Is to take the magnitude times the unit vector to get the force vector. Okay? Now, I want to make sure that we're all clear on this. How many force vectors are applied through point A? Not 3, 4. There's the balloon. These are the 3 unknowns, but there's still the balloon, right? So what I'm getting at is that I'm ultimately going to describe 4 vectors. And this one is the force in the balloon. So here's how I'm going to do this. So I've got my vectors and everything right here. By the way, what was FB? What was that? 800J? Is that what everybody said? Because it's pointing upwards. Remember, the balloon is going to be going straight up, so it's along the y-axis, and its magnitude is 800. So if I were to describe FB, it would be 800J. Bless you. Everybody good? Okay. All right. So when I do that, I want to make sure that's not coming out of thin air. Okay. So here's what I'm going to do. I'm going to say this one is negative 0.6. times the magnitude. This one times the magnitude. This is 0. This is 0. Maybe what I'll do is I'll get kind of comic with my parentheses. All right. So we'll do these. So these are all negative. That's TAC. And then this one is going to be 800 newtons. All right. We didn't get to finish our example on the video in class today. It looks like my tablet had overheated, so I want to go ahead and just knock the example out really quickly here in this separate recording, just to make sure that everything's preserved for posterity. Okay, so where we left off is we had these force vectors that we were writing, but we hadn't quite finished the K components. And as we recall, the K components are just going to come from up here. So this is going to be 0. This is going to be 0.5676 TAC. This is going to be negative 0.5077 TAD. And this is going to be 0. And these are going to be the K components. Oh. So now we have our four force vectors written, and again, all we're doing is taking the unit vectors here and multiplying them by their respective magnitudes. And then again, for F sub B, because the magnitude is 800 newtons, it's just 800 J. So if you want, we can go up here and say that, therefore, FB is 800 newtons times J, if we want to do that. We can put that up here. Okay. So now what we need to do is apply our equations of static equilibrium. So what we'll do is we'll just add up all of these components here. And these will be the sum of the forces in the x direction. And then add up all of these components here. And these will be the sum of the forces in the y direction. And then add up all of these. These will be the sum of the forces in the z direction. So I can start that down here. So if I sum the forces in the x direction, I'm going to get negative 0.6 TAB plus 0.3243 TAC. There is no TAD term, so I'm going to go ahead and put 0 TAD, just so I have that term for when I write this in matrix form. And so we'll call this equation 1. And then equation 2, we'll sum forces in the y direction. So again, we'll just add everything up in the blue box. And then plus 800 newtons equals 0. And then we'll just move the 800 newtons over. Okay. And then finally, summing forces in the z direction. So we have a 0 term here. To the minus. We can call this equation 3. Then we'll write it in matrix form. So, what do we got? Seven, 5, 6, 8. And then it's perfect for a solution in the Casio. When you input this in the Casio, of course, my phone rings during the recording. Okay, sorry, back to regularly scheduled programming. Okay, so we have our 3x3 system. We can solve this in the Casio by going to mode 5 and selecting option 2. And so essentially what we're just going to enter is this table. And when we do that, we get X is 200.91, Y is 371.69, and Z is 415.53. Or TAB is 200.9 newtons. We have TAC is 371.7 newtons, and then TAD is 415.5 newtons. And there you go. The method is pretty straightforward. One thing I did want to add to this recording that we haven't discussed yet, and it's not necessary for the exam or anything, but I thought it would just be nice to show you, is how you could solve these problems in Excel. So I'm going to pause the video and set up a quick spreadsheet and show you how to do this. So give me one moment. Okay. So I set up a quick spreadsheet with all of the data for this problem. So you can see here's the entries in matrix form. And what I've done is I've placed these here in the following cells. One thing to note is, since it's Excel, I went ahead and just did the internal calculation. So for example, instead of 0.3243, I actually went ahead and did the formulas. But I mean, if you go in and sort of make these a little smaller, you can see that it's the same values from the problem. So just to throw that out there. Okay, so I have let me make this a little bigger. So I have these cells here. Maybe we'll sort of box these, and we'll have these. So these are our set of equations, and we can solve this in Excel actually pretty easy with a couple of calculations. You can do them all in one step, but I'm going to do them in separate steps. So the first thing you need to do is you need to take the inverse of this matrix and then multiply it by this. So you can actually do that all in one step, but I'm going to do it separately. So what I'm going to do is I'm going to just go off here to the side, and I'm going to take the inverse of that big matrix by saying M inverse, and I'm going to take the inverse of all of this. Now, if you press enter, what that's going to do is it's actually going to spit the calculation into multiple cells. So it does what's called an array calculation. So you can see when you click the array that it all kind of highlights. And you can't really change like one quantity because Excel gets upset. So you sort of have to leave it alone. And then what you're going to do is go over here, and we're going to do a matrix multiplication of all of this and all of this. And then press enter, and there's your values. So what we can do is we can say, all right, let's squunch this a bit. And boom, that's the same thing that our Casio spits out. So you can do that way by using the M inverse command and then the M mult command. That'll work as well. I just want to show you that just to show you that there's another calculator that you can use, and that's Excel. But yeah, you can see that here's the values here, and we get the same values here in our Casio that we do here in Excel. And so there you go. There's the answers, and hopefully you find that's pretty straightforward. And that's all we have for this recording.